All right, we're going to continue lecturing here on chapter 14, never ending chapter. So last time we talked about several things. What those things were, who knows? I think it was pH minus the log of the H plus concentration. We did POH minus the log of the OH minus concentration. Remember the relationship here is the pH plus the POH will equal 14. We also obviously earlier on in the chapter there did our KW. Let's see here again. If you have the pH, you can get the H plus concentration from it by taking the inverse log of the negative pH. And same thing if you have the POH, you can get the OH minus concentration from it. Pretty much the same calculation. We talked about really the pH of a strong acid and base. So remember, because they are strong acids and bases, they will completely break apart. And really what you're looking for in terms of the pH is either the H plus concentration or the OH minus concentration. And I would say since most strong acids are monoprotic, the concentration of the acid would be the concentration of the H plus. For our bases, a lot of them are sort of like sodium hydroxide, potassium hydroxide. That would also be your concentration of your hydroxide. But if you had one like I think we did barium hydroxide or something like that, you may need to adjust the concentration to get the proper concentration of the hydroxide. Now, we then got into weak acids and pH, and weak acids and pH are pretty much just equilibrium type problems, which means that you should do an ice table. And really kind of the main difference in these type of problems is really what you're looking for, which is pH. So as you go through your ice table and you solve for X, X in this case would equal the H plus concentration, which would then allow you to go into the pH at that point and get it. We can solve these ice tables like any other equilibrium type ice tables. You can either make your assumption, you can do the quadratic or whatever it may be, but you'll get that X value. And typically that's what you're looking for is the pH of the solution. So that's kind of all you are sort of interested in. Remember that if you do make the assumption, like I think we talked about at the very end last time, you definitely should check it because again, it will not always work. And it is sort of concentration dependent, as we saw. The larger the concentration, you'll probably be okay in a lot of cases. But if you have a more smaller sort of concentration, it may not work out so well. Any questions on any of that there? The other thing we talked about obviously is weak acids are the only ones that will have Ka values associated with them as they will set up an equilibrium, and everybody else will not, like strong acids. So there will not be a Ka value for a strong acid. So as we just talked about there, pretty much same sort of idea in solving these problems. You want to identify the major species that's going to affect pH. In most cases, we could ignore the auto-ionization of water, and we pretty much will do that. So really what that means, for example, is in certain problems and sometimes in certain books, they will say like, the H plus concentration just from water itself is greater than, say, the acid or base maybe that you put in there. We're going to ignore any contribution from water in these type of problems affecting the pH. So basically the assumption is that we're going to do is all the H plus that you see in that solution is all going to come from either the acid or, the base in terms of OH minus. It has nothing to do with water in that sense. So everything's going to be determined by either the acid or base that's in that water. And we're not going to worry about sort of water's influence on it. Obviously, as we talked about, use the ice table there, solve for X, and again, get your pH. Let's try another one here to warm yourself up here for the upcoming exam. What is the pH here? 0.122 molar monoprotic acid. whose Ka value is 5.7 times 10 to the minus 4. Since they did not give you an actual formula, a generic formula for a monoprotic acid looks something like that, HA. All right, so take a few moments there, calculate it up, and see what you come up with. Okay, so let's take a look, see how you're doing here. So obviously we know a couple things as we talked about last time. We see a Ka value, thank you. That is a weak acid. So obviously an ice table should be the appropriate approach here. Once again, we're not really given a specific acid, so we can use this sort of generic formula of HA. When this does break apart, we will get H plus and A minus in this case. We write our Ka expression here, which would be our H plus times our A minus divided by our HA, and that's going to equal our 5.7 times 10 to the minus 4 in this case. We can do our ice table here. So initially 0.122, 0, and 0. Again, change here minus x plus x plus x. That means at equilibrium here, 0.122 minus x, x, and x. Any question on the table here? At this point, like normal, we're going to roll our equilibrium line into our expression here, and that will give us basically x squared divided by 0.122 minus x equals our 5.7 times 4. You could assume that x is equal to 0, and if you did that, hopefully you checked it because it is not so good at 6.8%. So you do need to kind of go back here and solve it another way. So again, a good reminder to make sure you do check it, as it will not always obviously work, and this is a case where it does not. So to solve it, we're going to multiply everything on the bottom there to the other side. That's going to give us basically x squared is equal to some numbers, 5.7 to the minus 4 times 0.122. 6.95 times 10 to a lot of zeros. 1, 2, 3, 4, 5, minus 5. And that's going to be minus 5.7 times 10 to the minus 4, I believe. We're now going to kind of bring everybody to the same side there so that we have our formula. So I'm going to go x squared is going to be plus a 5 point, and there should be an x there. 7 times 10 to the minus 4x. And then we're going to subtract 6.95 times 10 to the minus 5 is equal to 0. That obviously is going to be our A, B, and C there in our quadratic. So going into our quadratic there, x is equal to minus b, which would be minus 5.7 times 10 to the minus 4, plus or minus. Now, if we kind of do the square root part, I can take 5.7 to the minus 4, square it, minus 4 times a times c, and try that. Gonna give us here like a 2.78 times 10 to the minus 4. Once you square root it there, going to get us basically 0.01668. That's all going to be divided by 2 times a, which is 2. Going first in the positive direction here, negative 5.7 to the minus 4 plus 0.01668 divided by 2 gives us an x value of 0.00806. Doing the negative version here, that obviously is going to give us a negative number. That's going to give us a negative 0.00863. That's 0. I think I said it. I just didn't write the 8. So try that again. Negative 0.00863. Go. All right. So clearly here we're looking for pH, which is equal to x. So even though I miswrote it, it didn't really matter. That negative number is obviously not going to work here. That means that positive number there would equal our x, which should equal our H plus concentration, 0.00806. into our pH minus the log of it. Gonna yield us here 0.008, 806. There you go. Like a 2.09, looks like in this particular case. Any questions on any part of that there? So hopefully you can see, although they are Ka problems, they're really just still equilibrium problems, again, with the little addition of the pH sort of formula there at the end. Any questions? All right. Try one more here. What is the H plus concentration? And let's also do the pH as well. Why not? Of a 0.01 molar solution of HCN, Ka value there 6.2 times 10 to the minus 10. Okay, so let's take a look at this one. Once again, big hint there that is a weak acid as we have a Ka value. So we're just going to start here with our ice table. So we're going to break this guy apart into H plus and a little Cn minus action happening here. Initially, we got 0.01, 0, change minus x, and little 0.01 minus x, and x. We write our Ka expression here. It would be, once again, like normal, our products over our reactants. And that will equal our Ka value there, 6.2 times 10 to the minus 10. And now we can put all our values in. So we'll go x squared divided by 0.01 minus x equals 6.2 times 10 to the minus 10. That is a small value. So here I'm going to try my assumption again. And in this case, x squared over 0.01 equals 6.2 times 10 to the minus 10. Once again, I'm going to multiply to the other side, and then afterwards, I'm going to take a little square root action there. And if you do all that good stuff, multiplying first to the other side, 0.01 times 6.2 to the minus 10, and a little square root, going to give us an x value of 2.49 times 10 to the minus 6. We once again do want to check it, so we'll divide it by 0.01 and times it by 100%. And we're nowhere even near, I think, 0.1%. So this check here is good, yeah, in this case. All right, so since that check is good, that x value that we have here, as we get to see from our table, is equal to our H plus concentration. So our H plus concentration in this case looks like 2.5 times 10 to the minus 6. Does need a molarity there as it is a concentration. And that looks like it is number 2 on the list there. And obviously here our little addition, now that we have that H plus, we can go into our pH equation and solve for the pH. And in this case, this will give us actually a pH here of 560, looks like 5.60. Any questions on a calculation here, our weak acid calculation? Okay, so then let us talk a little bit about percent ionization and sort of what's going on with that. Good talk. Let's go back and talk a little longer. So percent ionization is the percentage at which really a acid breaks apart in solution, ionize or dissociates. It also can be applied to bases as well, how they break apart into OH minus. But percent ionization is the ionized acid concentration, which is basically the H plus concentration, divided by the initial concentration of the acid times 100%. It is actually how we check our assumptions. So this is basically how we check our assumption like we just did in the last problem. We got our X value, which was our H plus concentration. We basically divided it by the initial concentration times it by 100. So it's really the same calculation you do to check your assumption. And the idea here is, as we talked about, if we have a strong acid, it is again going to 100% ionize and basically break apart. Now, a weak acid, on the other hand, will not do that. It will mainly stay together, but will break apart a little bit. And this is what we were sort of talking about, I think, the other day as well. The initial concentration of our acid is important to the percentage that gets ionized. As we can see, if we have a small initial concentration, we have a relatively large amount of ionization that's happening. And that's the idea of like the pizza example I gave. You had 2 slices. If you take 1 slice away, you just took 50% of what you'd had there, right? And so there's a much bigger percentage that goes away. As we have a much larger sort of initial concentration of our acid, we have a lot lower of a percent ionization. And also back to the pizza example, if you have a whole pizza and take 1 slice away, you didn't just take a half of it, you just took a little bit of it away. There's still a good amount still there. So obviously that is why as well, in certain cases, the assumption will work, right? And in other cases, it will not work depending on really the combination of the initial concentration and also the Ka value. And that's why you should always, again, make sure that you check it. If we calculate percent ionization, we obviously could go into this formula. So let's take a look at a problem here and sort of how we might want to approach this. We have a solution that is 8 molar formic acid. It is 0.47% ionized. What is the Ka value here of formic acid? So a couple of things that we know about formic acid, which is it is a weak acid. Otherwise, we wouldn't be looking for a Ka value, right? So we kind of know that. So we could kind of approach it like a normal sort of Ka problem at this point. We could take our weak acid and break it apart there into H plus and a little formate action, I think. And initially here we have 8 molar of it. And we have 0, 0. Now, normally here we would do our ice table of minus X, plus X, and plus X. That means when we reach equilibrium here, we will have 8 minus X, X, and X. We could have our Ka expression here, which is our products over our reactants. In this case, though, that is once again what we're actually looking for in this particular problem. So normally at this point, what we would do, obviously, is take our equilibrium line and put it in there and solve for X. But we really can't do that in this particular case. So that's where really the other piece of information sort of comes into play, and that is the percent ionization. And as we just talked about, the percent ionization is the concentration of H plus basically divided by the initial concentration times 100%. So we actually could use that to figure out the H plus concentration. So we know that the percent ionization is 0.47% equals the H plus concentration. We know the initial concentration of our acid was 8 molar times 100%. So we basically will multiply the 8 to the other side and then come back and divide by the 100% afterwards. So we'll take our 0.47 times it by 8, divide it by 100, and that's going to get us here in this particular case 0.0376, and that will actually equal the H plus concentration, in this case 0.0376 molar. And again, that's what we get, obviously, from this calculation up here. Now that we have the H plus concentration, that's really helpful for us if we look at the ice table, because if we go down our ice table here, and we can see at equilibrium, the H plus concentration actually equals X. So although this is the H plus concentration, this would also be the X value that we have in our table. Kind of very similar to how we did the equilibrium experiment, where we kind of back calculated it. That means that it's this X as well, and it's also this X as well. It's all those X's in the table. And now that we can get numbers for each of these, we could actually go into our Ka expression. It would be basically 0.0376 times 0.0376 divided by our initial concentration. 8 minus 0.0376. And if we do all that there, that is going to get us our Ka value. And that will be something here with some numbers. And we'll go with 1.8 times 10. 1, 2, 3, 4, -4 here. So in this case, we could kind of use the percent ionization since it was given to us to sort of back calculate and figure out really the H plus concentration that's there at equilibrium. And from our ice table, as you can see, obviously that's all the X's and allows us to get to our Ka value. You obviously can just straight up use it as an equation and figure out the percent ionization of an acid, obviously, as well. Any questions on that one there? Yeah.
So we would be able to get the same exact answer if we didn't use that percentage, or would we end up getting the same answer?
The only way you would be able to solve this problem is you needed that piece of information about the percent ionization to allow you to get to the H plus concentration, or you would need some other piece of information to allow you to do it. Yeah.
This slide it says H plus over the initial concentration.
What's that?
Previous slide had more.
It's this one right here. H plus over the HA. I think I used that equation, I think. Oops. Are we talking here? Yeah.
They have that HCl.
Yeah. This guy here? Up here. The Ka expression, is that what you're talking about? That's just the Ka expression for the reaction, right? So it's products over reactants. Yeah. This is the percent ionization formula I used to calculate the H plus concentration right there, which is your H plus over your initial and then your percent ionization. But this is the Ka expression, just like a normal Ka equilibrium. And that's really what we use down here, obviously, to calculate the Ka value. Because that would be basically our H plus concentration. That would be our formate, and that would be our formic acid there on the bottom. Yeah. Yeah. It was just given to us right here in the problem that we started with basically a solution of 8 molar in this case. Yeah. Other questions? All right, then let's then talk about our friend bases. So obviously, if we have weak acids, we should also have weak bases, and we will have weak bases type problems. So for example, NH3, which is a weak base, a very common weak base, is basically going to accept that H plus over there. And it's going to form NH4 plus and OH minus. We could write an equilibrium expression for this, which is known as a Kb, adding to our ever-growing list of K values here. So with our Ka, now we have a Kb, and it's really still just an equilibrium expression. It is products over reactants here, so our NH4 plus, our OH minus, and our NH3. I will say that probably, unlike weak acids, where I personally don't put the water in the equation, it's probably a good idea to put the water in the equation for a weak base, so you could kind of visually see perhaps, it's going to accept it and how you get the OH minus. So I would recommend doing the water part here in the equation for a weak base, so you could kind of see it happening. Again, it's your option if you want to do it for the acid, but definitely for the base, I would put it in there. That way you could kind of figure out, kind of where the hydroxide comes from. In this case, just like Ka, if the Kb value is a larger value, it will be a stronger weak base in that sense. And for the same reason, because it is still an equilibrium constant, when we have that large value here of K, it means we should have products. And once again, if we look at the reaction on the product side, that would mean we have a lot more free floating OH minus in the solution, and that's going to make it a stronger weak base. Again, just like the weak acid sort of comparison of a weak base to a weak base, definitely a lot weaker than any strong base that's out there, like sodium hydroxide, potassium hydroxide. They are much stronger bases. But in comparison to the two weak bases, the Kb value that's larger would be the stronger weak base. They are particularly solved the exact same way as you do the Ka type problem. The main difference is in the equation, right? In the equation, if I were, for example, here to do an ice table here off of this equation, and I got whatever for, it don't really matter, 0, 0, minus x, 4 minus x, x, and x. When I solve for x in this case, if we go to our table, you have to remember that it actually equals the OH minus concentration. Again, not the H plus concentration. That means in this case, you might have to do an extra step here, which is first get the POH, then do a little 14 minus it, and you can get yourself to the pH here at the end. So you got to remember that it is the OH minus in this case. Also really important, as we talked about as well, all through the semester here so far, being able to properly write this equation is really important for you to solve it mathematically. I can't tell you how many times I've seen this equation written incorrectly and people end up with like H plus on the right-hand side or H3O plus, and it's a total base situation. And now you wrote the equation wrong and you're working it as an acid type situation. So super important to make sure that you're able to write these equations. It is part of your grade as well when you do things like an exam, is to be able to properly write these equations and stuff like that. So again, if that's something you have difficulty with, make sure you do take some time to properly get the equation down, because it's kind of like if you mess it up there, it could definitely throw off the entire calculation, because in your head, you'll be doing the wrong calculation. All right, so as this guy's yelling at us there, we get the OH minus, which gets us to the POH, and then obviously again to the pH. Here's a table for your book of some Kb type values. And let's take a look at a problem here and see. Amine compounds have a bad smell. Kb for this guy here is 5.6 times 10 to the minus 4. It has a, what is the pH? If we start with a 0.15 molar solution of this weak base. Okay, let's take a look here. So obviously it's a Kb, so it's a base situation. We're going to write our equation. And as I mentioned before, definitely with the weak bases, I would put yourself in there, the water. And again, you know this is a base, so it's going to accept the H plus. And again, you're basically just going to add an H plus over here, and that will be a plus. And again, that is where we're going to generate our hydroxide from over here on the product side. Any question on the equation there? All right, so the rest of it is kind of typical here. We could also write our Kb, which will be our products here. And that's going to equal our 5.6 times 10 to the minus 4. 11, it looks like, but 4. There you go. Initially here, 0.15, 0, 0, change minus x, plus x, and that means at equilibrium here, 0.15 minus x, x, and x. We're going to go into our Kb, gives us x squared divided by 0.15 minus x is equal to 5.6 times 10 to the minus 4. We could assume x is equal to 0, and of course you checked it and found out not so great at 6.1% in this case, so we do need to solve it another way. So we're going to do our quadratic one more time for good measure to warm you up for later. This is going to be x squared is equal to a little 5.6 minus 4 times 0.15. 0.000084 minus 5.6 times 10 to the minus 4x. Bringing everybody to the same side, x squared plus 5.6 times 10 to the minus 4x. That's going to be minus 0.000084 equals 0. Again, that's going to be our A, B, and C. Going into our quadratic here, we'll go with negative 5.6 times 10 to the minus 4 plus or minus. Once again, if we kind of do the square root inside first, 5.6 to the minus 4 squared minus 4 times A times C 0.000084. It's going to give us a 0.000336 inside before we take the square root. And after we take the square root, we will end up there with 0.0183, all divided by 2. Giving us our two x values here, we'll do the plus first. And that's going to give us a x of 0.00887. And we'll do the minus next, which obviously, once again, is going to yield us a number we don't really want anyways. But just in case you like the number, that is going to get us here negative 0.00943. Once again here, that's not going to work for us, which means that that is going to be our number. Also important, as we talked about there, is this is the OH minus concentration, right? So that X there is the OH minus concentration, 0.00887. Remember, now we could get the POH, which will go right there in the middle of my ice table. Why not? Log of 0.00887. Thank you, 2.05. And then obviously here we could just take our 14 minus it there to get our pH. Obviously as well, if for some reason you were thinking in your head, or maybe you wrote the equation wrong or something like that, and you thought that that was the pH of 2.05, obviously it should not make sense. This is a base, right? So obviously here subtracting 14 gets us at 1195 here, which is definitely basic and does make a little bit more sense obviously here. Any questions on those steps? Yeah. So again, a couple of good reminders today to make sure you do check your assumption to make sure that you are doing the calculation correctly. Any questions? All right, so let's talk a little bit about Ka and Kb type of numbers here. And if we look at the equation here for the first one, this is a weak acid, which we would have a Ka expression for. And here's a weak base there, which we would have a Kb expression. And in this particular case, a couple of things are really important. There will definitely be times where you may be given a Ka value or a Kb value, and you actually need the opposite one. You need either the Ka or Kb, the different one that you're given. And also sometimes people, going back to sort of writing the equations correctly, and why it's really important is, if you write the equation correctly on the product side, if you see H plus or H3O plus, that means you should definitely be using a Ka value here when you're doing any type of calculation. Similarly, if you write the equation correctly, which hopefully you should, and you see hydroxide over there on the product side, you definitely should be using a Kb type of number. There are specific problems where, frankly, they give you the wrong K value, and you do need to get to the right K value when you do it. And again, that's why writing these equations are really important, so that you know when you look at it, oh, I should be using a Ka value or a Kb value here. We take both of these things together and we add these reactions together, we get really the overall reaction that's happening here, in a sense, is we basically make water, which has its own K value, as we know, which is Kw. And that is that 1 times 10 to the minus 14 action. So one way that we can go from a Ka value to a Kb value is to use Kw. And we will use this a lot in a number of different problems where, as I mentioned, they kind of give you the wrong K value there to use. So If you have the Kb but need the Ka value, you can take 1 times 10 to the minus 14 and divide it by the Kb value, and vice versa. If you have the Ka value, you want the Kb value, you can take 1 times 10 to the minus 14 divided by the Kb value in this particular case, and it's really the same calculation. This also is kind of helpful sometimes. Perhaps maybe you only have a Ka table and you need the Kb for the thing, so you can kind of flip it to what you need. It does get a little tricky, as we'll talk about a little later on as well, when you're dealing with diprotic acids or polyprotic acids. You got to make sure that you kind of choose the correct value to change. If it's monoprotic or something like that, and there's only one hydrogen, you don't really have to worry too much about it. But there are certain situations where you have to kind of make sure you grab the correct K value to sort of flip, if you will. Any questions on that? So that's definitely something we will see a little bit later on when we talk about salts and hydrolysis type reactions. They're very historically give you the wrong sort of K value and you have to switch it out. Let's talk a little bit about acid strength here first off. And when we look at acids and we look at acids that do not contain oxygen, one of the major things that we look at to determine which one is a sort of stronger acid is actually bond enthalpy or bond energy. And you might have talked about that when you did bonding. All the bonds you break minus all the bonds you make, and the difference is the delta H of the reaction based on bond energy or enthalpy. And it's actually bond strength that we look at. And the stronger the bond strength, the weaker the acid is. And that is because you just logically think about it. What makes something an acid in this case is the ability to break that bond and release that hydrogen into the solution as H plus basically floating around. So the stronger the bond energy is, the harder it is to break that bond, which means the H is going to hang on there a lot longer and less of it's going to come off into the solution and will make it actually a weaker acid. So when we look at group 7, sometimes people think it might be based on electronegativity, but in this type of acid, it's actually based on bond enthalpy. And HF bond actually has the highest bond energy. The HI bond actually has the lowest bond energy. So when you're comparing something from like HF to HI, it is much harder to break this bond than it is the bond here. It's about almost 2 times or 3 times less harder to break it. So this guy here is going to come off a lot easier and thus making it a strong acid. So when we look at acids that don't contain oxygen, which is pretty much group 7 on the periodic table, acid strength actually increases as you go down the group, which is why HI is actually added to our list of strong acids because they're actually stronger than, say, HCl, and HF is a much weaker acid in that case. Now, when you're looking at acid strength, and here's a little table from your book that also describes that. Again, acid strength increasing to the right and kind of decreasing down the group there. When you look at acids that contain oxygen, these are sometimes referred to as oxyacids because they do contain oxygen. They typically will have this bond here, an OH bond. And in that case, it's really this bond that we want to break to sort of release that H plus into solution. Remember that the OH bond is also a polar bond, right? And again, the oxygen being more negative, and that means that obviously difference in electronegativity values, the oxygen is kind of bringing more of the electrons towards itself. Now, when we look at this type of acid that has oxygen in it, we look at really 2 things, and it depends on the situation as to which one you will look at. We look at either the electronegativity, which a reminder, right, when we look at the periodic table, electronegativity increases this way. And decreases as you go down. And the other thing that we sometimes will look at is the oxidation state or oxidation number, which you may be a little familiar with, hopefully. And that's sort of the charge that each of these elements would have based on how they're sharing electrons, who they're sharing electrons with. And an oxidation state and number is not necessarily the charge that you sort of think about in an ionic situation always, but it's sort of in a covalent situation, sort of the charge that they take on as a result of who they're sharing electrons with. So for example, here, if we look at an acid here that has oxygen. And if we look at the central atom here, the central atom has the same oxidation number. And just to show you again, perhaps how to do oxidation number, oxygen is a good place to start. That's -2. So all these would have a -2 oxidation state. Hydrogen is +1. And when you add up all the oxidation numbers, it should equal the overall charge, which in this case is neutral. So that's 2, 4, 6, and +1 is -5. That means the chlorine in this case actually has an oxidation number of +5. Same thing over here, -2, -2, -2, and +1. Once again, that's going to be -6 and +1 is -5. And to balance it out, the bromine also has the same oxidation number. So in this case, because the central atom in each of these acids have the same oxidation state, we clearly cannot use that to distinguish which one is a stronger acid versus a weaker acid. And once again, we're looking at really this bond right here that we're trying to break, which again is a polar bond with the electrons heading in. So in this case, where we have the same the same oxidation state of the central atom, we then actually look at electronegativity of the central atom. And in the case between chlorine and bromine, chlorine is more electronegative. So what does that mean? It means that already the electrons are heading towards the oxygen. And now you got this chlorine, which is going to bring the electrons even kind of closer in towards the chlorine. And that's going to essentially just continue to weaken this bond and allow this H plus to come off a lot easier than the least electronegative guy in this case between these two, the bromine, which will also bring the electrons in, but not to the same extent. So when comparing these two things here, because chlorine is more electronegative and they both share the same oxidation number, the guy that has the chlorine would actually be the stronger acid of the two. And between these two here, the HClO3 would be a stronger acid than the HBrO3. Questions on that there? So acids with oxygen, same oxidation state of the central atom. The thing that you should then look at is the electronegativity of the central atom. The one that is greater in terms of electronegativity will be the stronger acid, because it would be much easier for that H basically to pop off of that bond. Now, the opposite is a little bit true here, or a little bit different when we have an acid with oxygen and the central atom does not have the same oxidation number, but they are the same sort of group. In this case here, we have all chlorine as their central atom, which means clearly they're all going to have the same electronegativity value, so we can't use electronegativity to determine that. So here we would actually use oxidation state of the central atom. In this case here, all these oxygens are -2, -2, -2, -2, and the hydrogen is +1. So that's a -8 and a +1 is a -7. The chlorine here is a +7 oxidation state. Here is -2, -2, -2, +1 like we did in the previous problem. That's -6 and +1 is -5. To balance it out is +5. Here's -2, -2, +1. That's -4 and +1 is -3. So the chlorine here is a +3. And lastly, -2 and +1. We're going to have a +1 oxidation state here. Now, as you can see there, chlorine has positive oxidation states in this case, rather than maybe what you normally think of the charge on chlorine, which is -1. And it is -1 in an ionic compound where the electrons are completely transferred from the metal to the non-metal. It will gain that electron and have a -1 charge. In this case here is not an ionic compound, and none of these. They're all sharing electrons, and because they're sharing electrons with electronegative atoms, they will take on a more positive oxidation state, because frankly, all the electrons are sort of heading away from them and they're getting pulled to all those oxygens. And that's going to make it more positive in this case because of who they're sharing electrons with. And obviously, as you see down here, how many they're sharing electrons with. So the idea here is the greater the positive sort of oxidation state, the stronger the acid would be. So for example, here, again, the electrons are being pulled in this direction. but it's only feeling like a +1 pull for this chlorine, so it's going to come a little bit further in, as opposed to over here where the electrons are heading in this direction, but it has a pretty big positive charge hanging out there on the chlorine, which is going to attract those electrons in a little bit more. Once again, going to allow this bond to be much, much weaker and easier for that H plus again to come off in this case. So when comparing acids that have oxygen, they have kind of very similar electronegativity values. We look at oxidation number, and the one with the greatest oxidation number would be the stronger acid. So this would be the stronger acid, the next stronger, and at the end here would be our weakest acid in terms of our HClO. Any questions on acid strength? All right. Good place to stop, I think. We'll let